All right, let's just dive right in with a high-stakes problem. Imagine a bacteria culture that doubles every single hour, and you're starting with a baseline of exactly 500 bacteria. How many are going to be there after 12 hours? Can you mentally crack how fast these microscopic organisms will multiply before we even go over the mathematical formulas? Just keep whatever number you're guessing in your head, because we're going to solve this mystery together very shortly.
Welcome to This Explainer. Today we're taking what usually feels like dry, abstract algebra and transforming it into the hidden formulas that dictate absolutely everything around us. We're talking everything from the compounding interest in your bank account to the biological growth happening at a petri dish.
Here's what we're getting into today. We've got the power of patterns, arithmetic versus geometric sequences, adding it all up with series, taming infinity and sigma, and finally, sequences in the real world. Let's get to it.
Section 1. The Power of Patterns.
So let's start with something you're already doing without even cracking a math book. Your brain is practically hardwired to find patterns in the noise. Quick, what comes next? 3, 6, 12, 24. I'm willing to bet your brain is already firing, trying to solve the puzzle. You're intuitively looking at the gaps, measuring the jumps, and testing relationships without even thinking about it.
It's 48, and you probably got that pretty fast. Humans are absolutely wired to find the underlying rule. This perfectly proves that before we do any of the heavy lifting with complex math today, we're really just formalizing a survival skill you use every single day. You intuitively knew we were just multiplying by 2.
Now, we just need to get our mathematical vocabulary locked in so we can actually talk about these patterns. An ordered list of numbers that follows a reliable rule is officially called a sequence. And every single individual number inside that list, that's simply called a term. Okay, so mathematicians use two different ways to describe these rules. You've got the term-to-term rule, which basically tells you how to get from one number to the very next one, like, hey, just add 3. But the nth term rule, that gives you a master formula to find any term you want instantly. Think of the term-to-term rule like walking up a staircase, step by step. Sure, it works, but it takes forever. The nth term rule is like a mathematical time machine that lets you teleport straight to the 100th step.
Think of this as your ultimate cheat sheet to the universe's most common mathematical codes. You've got your arithmetic and geometric sequences, which we're going to dig into heavily today, but you also have natural patterns built on square numbers, cube numbers, the wildly unpredictable prime numbers, and of course, the famous Fibonacci sequence, where you just add the two previous terms together to get the next one.
Section 2. Arithmetic versus geometric sequences.
Let's see how this pattern recognition builds into the two heavyweight champions of sequence math. This is absolutely crucial to internalize. Arithmetic sequences always have what's called a constant difference, we call it D, and they rely entirely on addition or subtraction. Geometric sequences, on the flip side, have a constant ratio, or R, and they're all about multiplication or division. So think of arithmetic sequences like walking forward with a nice, steady stride. Geometric sequences? That's like strapping yourself to a continuously multiplying rocket ship. The growth curves are just radically different.
But hey, no matter which rocket ship you take, you need a launch pad, right? That starting point is always, universally, represented by the letter A, the first term. Whether you're working with the linear arithmetic formula or the exponential geometric one, A is where it all begins. You plug it in, apply your constant difference or ratio, and just let the algebra do the heavy lifting.
Now, here's a fun twist. Remember our opening mystery about the bacteria culture? That's actually just a geometric sequence waiting to be solved. We started with 500 bacteria, so A is 500. It's doubling, so our common ratio R is 2. But watch out for this trap. Because we started hour 0 with term 1, after exactly 12 hours, we're actually calculating the 13th term. Let's see what happens when we run those numbers through the formula.
Over 2 million. 2,048,000 to be exact. After just 12 hours of simple doubling, that tiny initial batch of 500 bacteria exploded into a massive, sprawling colony. And honestly, that is the terrifying and awesome power of geometric growth. It sneaks up on you. It starts deceptively slow, but once it starts compounding, it literally skyrockets.
Section 3. Adding it all up, series.
Okay, so we know how to predict the future of any individual sequence, but what if we want the grand total? What if we add all those numbers together? First off, a major warning here. Do not mix these two concepts up. A sequence is just your ordered list separated by commas, like 2, 5, 8, 11. A series is what happens when you take those commas out and smash the plus button between every single one of them. Remember, a sequence is merely a list, but a series is a total sum.
Now, mathematicians love efficiency. They hate writing out massive page-long addition problems, so they use sigma notation. See that giant, sharp-looking Greek letter sigma? That's literally just a highly compact way of saying, hey, add all this stuff up. The little numbers at the bottom and the top of the sigma just tell you exactly where your addition starts and where it stops. I know it looks intimidating, but it's really just a neat little set of instructions for a sum.
Section 4, Taming Infinity and Sigma. All right, buckle up for this one, because we're about to push this math to the absolute infinite limit. What happens when we never stop adding? Seriously, look at this infinite string. 1 plus a half plus a quarter plus an eighth, going on literally forever. Logically, your brain is probably screaming that if you add positive numbers forever, it eventually has to equal infinity, right? The pile just has to keep getting bigger and bigger without end.
Nope. Boom. The answer is exactly 2. How? Because our common ratio here is 1/2, which is crucially less than 1. That means the numbers you're adding get incredibly tiny, incredibly fast. This massive, infinitely long series collapses perfectly down to just the finite, tidy number 2. It's a completely mind-bending concept, but it's a huge bridge into advanced calculus. It proves that an infinite, never-ending process can actually have a perfectly finite boundary.
Section 5, Sequences in the Real World. Let's bring our mathematical rocket ship back down to Earth for a second. We're talking population growth, compound interest, loan repayments, computer algorithms, radioactive decay, business forecasting. These are not just dry textbook formulas meant to torture you on an exam. These sequences are literally the hidden machinery running modern society. They're calculating the devastating interest on a bank loan, modeling carbon dating, and making sure the complex computer code you rely on runs flawlessly.
But before you go out and conquer the world with this, you have to guard yourself against some classic traps. Confusing your common difference d with your common ratio r will completely wreck your math. And whatever you do, don't accidentally use an arithmetic formula on a geometric sequence. That's like bringing a bicycle to a space race. Also, don't forget that your first term is always a. And please, don't mix up your sequence lists with your series sums. These pitfalls catch even the very best students off guard, so burn these rules into your memory.
So here's my question for you. The next time you look at a complex, sprawling pattern out in the real world, maybe it's the arrangement of petals on a flower, the wild swings of the stock market, or even how fast a trend goes viral, are you really seeing random chaos, or are you just looking at a beautiful structured sequence whose nth term rule you just haven't cracked yet? What's the secret formula hiding right beneath the surface? Keep looking for the hidden code, and thanks for joining me on this explainer.